Hey everyone, I am Miss Hu, your physics teacher. In this video, we're going to go through the calculations involved when it comes to the calibration of uncalibrated thermometers. So what we'll be learning is how to calibrate a mercury thermometer and how to apply the formula to calculate an unknown temperature from an uncalibrated thermometer. Now, if you're wondering what it means by uncalibrated thermometer, we'll get to that in a moment, but first things first, we're going to learn why we use mercury in a thermometer. So mercury thermometers were very popular at one point. Now they're less popular because we found better liquids that we could use, but for some of you, you may still need to learn this in your syllabus. So why we use mercury in a thermometer? For one, mercury is a liquid at room temperature, which enables it to be able to expand and contract. That means it's able to change volume. And in terms of its expansion and contraction, mercury is able to do this quickly and uniformly. So this enables us to get the temperature really quickly, so we don't have to wait a long time. And with the uniform expansion and contraction, it enables us to come up with a linear scale. That means once we've come up with the scale, we're able to divide this into equal values, making it easy for us to get a reliable scale. Mercury also does not stick to glass. That means as the mercury changes volume, the mercury pulls away from the glass, enabling us to get a very clear view of where its current level is. If the liquid stuck to glass, then we might get the wrong information because the liquid may be stuck to the glass, it's actually gone down, but because it's stuck to glass like water, we're reading the value at a higher position instead of the actual lower level. The reason why mercury is able to expand and contract quickly is because it is a good heat conductor. That means it has low specific heat capacity. This enables mercury to change temperature very quickly to match the temperature of the material that we are measuring, and therefore it's able to give us the temperature quickly and correctly. Now, let's go into the concept of an uncalibrated thermometer. So when we talk about calibration, to calibrate a measuring instrument means to make sure that its scale is correct. So if, let's say, the thermometer was showing 100 degrees Celsius, the actual temperature is 100 degrees Celsius. This applies to any measuring instrument. So for example, if you have a measuring balance that shows a value of 20 kilograms, that means the actual mass that is being measured is 20 kilograms and not another number. So if you have a measuring instrument that's showing you the incorrect value, so for example, if you place a 50 kilogram object on the measuring balance and it shows you 45 kilograms, it's not correct, it's 5 kilograms off. That means the calibration is no longer accurate. So from time to time, you may find that you need to calibrate your measuring instruments just to make sure that the reading is accurate. But if we have just built a measuring instrument, there may be no scale on it. So for example, if we were to build a mercury thermometer, we could build it with all the necessary components. For example, you could have the bulb with the mercury inside, the capillary tube that lies inside the glass tube, and the capillary tube is hollow, allowing the mercury to expand and contract within the capillary tube. The construction is there, but the scale is not. So this is an uncalibrated thermometer because there is no scale. So if we want to calibrate this thermometer, it means that we want to be able to put the accurate scale on this blank thermometer. So how do we calibrate this thermometer? Now it is possible to get another accurate thermometer, and we would use that thermometer, get the temperature that's shown on that thermometer, and then put the same marking on the thermometer and so on and so forth. So say we want to calibrate this thermometer without the use of another thermometer. It is possible, but you must get two values of temperatures that are easy to obtain and guaranteed to be accurate. So let's think. Which temperature is very easy to obtain, and you know even without measuring its temperature, you know for sure that would be the exact value of the temperature? That's right. If you use water and you observe its change of state, you'll be able to get its accurate temperature. So for one, we know that ice melts at 0 degrees Celsius. So if we were to place this thermometer within melting ice, we know that the temperature shown on this thermometer would be 0 degrees Celsius because ice melts at 0 degrees Celsius. pure ice. That means it's pure water, no impurities. It melts at 0 degrees Celsius. So if you could get pure ice and you place the thermometer within that ice and observe it when it melts, the temperature shown is 0 degrees Celsius. So when we place this thermometer in that melting ice, we make a marking at the mercury level. That level of temperature marked on the thermometer would be 0 degrees Celsius. Likewise, if we were to place the same thermometer in boiling water, so I'm just going to draw that here, and we're going to add some heat just to show, hey, it's boiling. We know that pure water boils at 100 degrees Celsius. So when we place the thermometer in water and the point where it starts to boil, you see all those bubbles. That's showing that it's boiling. We know that the thermometer is showing a temperature of 100 degrees Celsius. So from this, we make the marking on the thermometer at where the mercury has risen to. We know that the temperature shown at this point is 100 degrees Celsius. Because these two values are very easy to obtain, these are known as fixed points. The lower point of 0 degrees Celsius is known as the ice point, and 100 degrees Celsius is known as the steam point. So because the value of 0 degrees is lower, it's commonly known as the lower fixed point, while 100 degrees Celsius is known as the upper fixed point. In case you're wondering, wow, it's so perfect. Ice happens to melt at exactly 0 and water happens to boil at exactly 100. You must remember that measurement is a human construct. So the reason why ice melts at 0 and water boils at 100 is because we chose it to be at 0 and 100. So the Celsius scale is built based on the melting point and the boiling point of water. Now, before we move on, I just want to point out to you that in some syllabi, they don't put the thermometer in melting ice and in boiling water this way, but rather they put it in this kind of setup. It's pretty much the same thing. So instead of placing the thermometer within a cup or a beaker of ice, we place the thermometer within ice that's placed in a funnel. So that way we can actually see whether the ice is melting or not. Because once the ice starts to melt, you'll find that the melted water would drop out of the funnel, and of course you must place a beaker underneath to catch the melted water. So at the point when we start to see water coming out from the funnel, the ice is melting. That guarantees us that it is at a melting point. So this would be 0 degrees Celsius. Likewise, for boiling water, what we do is we would place the thermometer not within the water, but in the space above the water, which we will boil. Why? Because when the water starts to boil, then of course the water turns to steam, and steam would be at 100 degrees Celsius. That means within this round bottom flask, as we heat up the water, when the water turns to steam, the thermometer will be able to measure the temperature of the steam, and that would guarantee that the thermometer is actually measuring 100 degrees Celsius. So some syllabi might use these diagrams, some syllabi might use these diagrams. In the end, it all comes down to the same thing. What we want to find is just the ice point and the steam point. That means the melting point of water and the boiling point of water. So now that we know where the 0 and 100 degrees Celsius points are on the thermometer, how do we get the other temperature values? So that's why we need to use a liquid that expands and contracts uniformly. That means every change in 1 degree Celsius would have a uniform expansion or contraction of the volume. So for a mercury thermometer, because we're using a capillary tube, it is true that the mercury's volume is the one that's changing. However, we don't usually measure volume because it's a little bit difficult. Because a capillary tube is uniform in its cross-section, one physical quantity we can measure in this case is not the volume of the mercury, but the length of the mercury column. So what we can do is we will measure the length between 0 and 100 degrees Celsius, and then we divide this into 100 equal spaces, and each spacing would represent the change of 1 degree Celsius on the scale. Okay, you get the idea. And that's how we can calibrate the scale on this uncalibrated thermometer. So this is an image I have borrowed from physicsclassroom.com just to show you this is how we calibrate a thermometer measuring in degrees Celsius. So we place the thermometer in melting ice that would show us 0 degrees Celsius, and we place the same thermometer in boiling water and that would show us 100 degrees Celsius, and then we make 100 equal divisions between 0 and 100 in order to come up with the Celsius scale on this thermometer. Now the formula for calculating the temperature of an uncalibrated thermometer. So what we've covered in the earlier slide is the practical way of how to calibrate an uncalibrated thermometer. But for your exams, very often they will give you this question where it's an uncalibrated thermometer and you've got to figure out the temperature from there. So you can think of it as someone has this uncalibrated thermometer, they have measured the 0 and 100, but they're just too lazy to draw all those divisions out. So instead, they're going to be measuring the length of the mercury column. So to calculate the temperature, it will be based on the length of the mercury column that is shown when taking the temperatures. The formula is this. Theta is the unknown temperature. We'll take the length at the unknown temperature minus the length when the temperature is 0 degrees Celsius. Divide this by the length at 100 degrees Celsius minus the length at 0. And we'll multiply this with 100. So this is the formula. So in this formula, what do all these symbols mean? What's theta? What's L theta, L0, L100? What's all that? Let's look at this uncalibrated thermometer and find out how to obtain all these values from that diagram. Okay, so now let's recall, when calibrating this uncalibrated thermometer, we must have two fixed points, the ice point and the steam point. So I'm going to make a marking here. This is 0 degrees Celsius. I'm going to write it on the left side. And 100 degrees Celsius is, of course, on the upper part. Now remember that I mentioned earlier, the division is actually based on the measurement of the length of the mercury column. So when we talk about measuring the length, like in this case, the formula here uses L. What is L0, L theta, L100? What are all these? Now, a common mistake a lot of students make is that they think that 0 degrees Celsius is right at the beginning of the bulb. That's not true. Mercury is still a liquid even below 0 degrees Celsius. And when we design the thermometer, it is possible for the length of the capillary tube to extend below 0 degrees Celsius. So 0 may start somewhere at a distance above the mercury column. So L0 is actually the length of the mercury column at 0 degrees Celsius. So how we measure L0 is from the bulb to the marking of 0 degrees Celsius. So that's what we mean by L0, the length at 0 degrees Celsius. So L100 is the length between the 100 degrees Celsius mark and the same starting point of where we measured L0, like this. So theta is the unknown temperature. That means, say for example, we took this thermometer and we place it into a substance or a liquid where we don't know the temperature. We want to find it out. So obviously the mercury column is going to extend to that particular temperature position. So let's say the mercury column extends up to this point. So say this is the unknown temperature, which I will label as theta degrees Celsius, and that's the temperature that we are looking for. L theta refers to the length of the mercury column between this unknown temperature and of course the same starting point. So that's L theta. So when we want to use this formula, these are the values that we need to recognize and substitute into this formula. Now, in the next slide, I will show you how to use this formula to solve a question. But before that, I'd like to share with you another method to figure out the temperature of an uncalibrated thermometer. Because let's say you can't remember the formula and you're like, okay, what do I do now? So I'm going to show you a ratio method. And this ratio method is actually how this formula was derived. So when it comes to ratio method, let me just draw a line here to separate this, to show you clearly. Now, to use a ratio method, honestly speaking, you have to be quite good at math and you have to understand ratios quite well. If you're not so good with math and ratio, then it's okay to stick with the formula. But for the benefit of those who want to give this a try, let's go through this right now. The ratio method works because of mercury's property of being able to expand and contract uniformly. Because the mercury has a uniform change in its length, we can assume that the ratio of the change in the temperature would give us a uniform change in the length. Now, in order to obtain the value, we need to compare the unknown against the known. So let's start with the known first. So for the known, so remember we're going for the difference in value. The known value here is the difference between 100 and 0. So the difference between 100 and 0 degrees Celsius is 100 degrees Celsius. I'm going to write that on the left side here. And this ratio is equal to the difference in length between 100 and 0. The difference in length, that means we want to get this value, which I'm going to write as L1. Now, L1 is a known value because you'd be able to measure it because you know the length between 100 and 0. You can just measure it using a ruler. Now, compare this against the unknown. So the unknown in this case is theta. But remember, we're not taking theta directly. We need to take the difference in temperature. So the difference between theta and 0, theta minus 0, you get theta. This ratio would be equal to the length between theta and 0. So I'm going to mark this as L2. Because of the uniform expansion, we can assume that these two ratios are equal. And mathematically, if you recall, you can change the ratio into fractions. So we can write this as 100 divided by L1 equals to theta divided by L2. If we rewrote this so that theta becomes the subject, we would get theta equals to 100 times L2 divided by L1. Now, if we look at what L2 and L1 are, I'm going to put 100 out here. And let's keep the fractions for L2 and L1. So L2 goes on top. What's L2? So as you can see, L2 is quite simply the difference between L theta minus L0. Whereas L1 is L100 minus L0. And if we were to compare this formula against this formula, you can see that they're exactly the same. So that's how you can use a ratio method to figure out the answer. So whether you use the formula or the ratio method, both work. Now, in case you're wondering, isn't the ratio method just exactly the same as the formula? So we're going to look at the next slide, how you can use a ratio method without memorizing the formula or even deriving the formula in the first place. Let's look at how to solve a problem. The length of a mercury column in an uncalibrated mercury thermometer is 3 cm when its bulb is immersed in melting ice. When the thermometer bulb is placed in steam, the length of the mercury column increases to 28 cm. What would the temperature be if the length of the mercury column is 23 cm? So I'm going to show you how to solve this problem using the formula right away, or we can use the ratio method. Now, when solving this kind of question, normally I like to draw a very simple diagram so that I can visualize very quickly what all these values mean. So let's say this is the mercury column and it's a mercury bulb. So this is just representing a very simple mercury thermometer. Now, melting ice, as we know, is 0 degrees Celsius. So I'm going to write here 0 degrees Celsius, and this is 3 centimeters. Now, the steam point is 100 degrees Celsius. So I'm going to mark that 100 degrees Celsius, and this is 28 cm. The unknown temperature, which is theta, is at a length of 23 cm. So in order to solve this problem, we can use a formula, which is theta equals to L theta minus L0 divided by L100 minus L0 times 100 degrees Celsius. So you have to know what L theta, L0 and L100 are. This visual enables us to see very quickly what all these values are. So L theta is the length at theta degrees Celsius. So that's 23. So I'm going to substitute that straight away. This is 23. L0 is the length at 0 degrees Celsius. So that's 3. L100 is the length at 100 degrees Celsius. So that's 28. And L0 again is 3. So 23 minus 3 gives us 20. 28 minus 3 gives us 25. So when you solve this, you should get 80 degrees Celsius, and that's the answer. Now, let's say you're like, oh gosh, I can't memorize the formula. There's too many formulas to remember. But don't worry, miss. I have excellent math skills. I completely understand ratio. All right, so let's give the ratio method a try. Now, for the ratio method, one thing I like to do is I like to write the values out. Drawing this visual, of course, really helps. But here's an additional thing I like to do. I also like to write out the matching temperatures to the length. So how I would write it is like this. At 0 degrees Celsius, the length is 3 cm. At 100 degrees Celsius, the length is 28 cm. And at the unknown temperature, it's 23 cm. Now, why I want to write this out is because solving by ratio, we need to get the difference in the value, the change in values, not the actual absolute value. So we need to compare the difference in temperature against the difference in length. So when we talk about the difference, that means we're not taking the value of 0 and 3 cm or 128 cm. No, we're looking at the difference between these values. So remember, for ratio, we always compare the known against the unknown. So let's start with the known first. So we're going to take the difference between these two values. So on the left-hand side, we're going to write the difference in the temperature. That means 100 minus 0. Then on the right-hand side, we'll take the difference in length. So the difference between 3 and 28. So 28 minus 3. This ratio would be equal to the ratio between the unknown, which would be the difference between these two. Now, can we actually take the difference between 100 to theta instead of 0 and theta? Yes, you can. It's just that it becomes a little bit more difficult to calculate, because if you're going to take the difference between 100 and theta, you have to take 100 minus theta or theta minus 100. It's much easier to take it between theta and 0, because anything minus 0, that you get the actual value. So theta minus 0, you get theta. So that's why we take the difference between 0 and theta. It's just an easier math calculation. So we will take theta minus 0, and this would be ratioed against the difference in length, which would be 23 minus 3. So you'd get 100 ratio to 25 equals to theta ratio to 20. So remember that when you have a ratio, you can convert this to fractions. So what we'll get is 100 divided by 25. This is equal to theta divided by 20. We will rewrite this, making theta the subject. So 100 divided by 25 times 20. Solving this, you would also get 80 degrees Celsius. So yes, as you can see, you get the exact same answer, whether you use the formula method or the ratio method. Now, this method does not work only for mercury thermometers. This can be used for any thermometer which shows a linear scale. That means the changes in the physical properties is uniform compared to the change in temperature. So some other thermometers would include the resistance thermometer, pressure thermometer, and thermocouple. If you come across thermometer questions that are not mercury thermometers but are these kind of thermometers instead, you can still solve them using the same methods. That means you can use the formula or you can use the ratio method. So let's start off first with an example of a resistance thermometer. So for a resistance thermometer, its resistance changes with temperature. So the higher the temperature, the higher its resistance. So assuming that this thermometer has a uniform change in resistance, we can use the same calculation methods. When placed in melting ice, the resistance of a wire is 10 ohm. The same wire has resistance of 35 ohm when placed in steam. What is the resistance of the wire at temperature of 45 degrees Celsius? So in this case, I won't be drawing out the skeleton of the mercury thermometer because that's weird, but I will write down the corresponding temperatures with the resistance. So that way we're able to see the values that we need to use accordingly. So we know that in melting ice, the resistance of the wire is 10 ohm. So I'm going to write here at 0 degrees Celsius, resistance is 10 ohm. Now in steam, that's 100 degrees Celsius. So I'm going to write here 100. This is 35 ohm. Now, the unknown is no longer the temperature, it's a resistance. So we know that the temperature is 45 degrees Celsius. Unknown temperature, I'm just going to put this as R. Let's put R45, indicating that's a resistance at 45 degrees Celsius. Can we use the formula to solve this question? Yes, we can, because the two fixed points are the same value at 0 and 100. But we do need to make some modifications to the formula because this is not the length, it is now resistance. So we're just going to rewrite the formula. I'm going to write it over here on the left. Instead of writing L, we're going to write R because length doesn't make sense in this case. It's resistance. So R unknown, so R theta minus R0 divided by R100 minus R0 times 100 degrees Celsius. So the unknown temperature is now known. It's 45, so we're going to put that in theta, 45. R theta is the unknown, R45. R0 is the resistance at 0, so that's 10. R100 is 35. R0 is 10. And we're going to multiply this with 100 degrees Celsius. So now let's solve this. So we have 45 equals R45 minus 10 over 25 times 100. So now I'm going to move my face out of the way. Okay, we're going to make R45 the subject, but I'm going to do this step by step for those who may need some time to understand this mathematical process. So I'm going to keep this as R45 minus 10. So we need to bring 25 up and 100 down. That gives us 45 times 25 divided by 100. And this gives us 11.25. So to get the resistance, we take 11.25 plus 10, and that's 21.25 ohm. And that's the answer. Before you say, yay, I've got the answer, always check, is this a logical value? So we know that the resistance at 0 is 10, and the resistance at 100 degrees Celsius is 35 ohm. Because 45 is between 0 and 100, that means the resistance must be between 10 and 35. Then check, is 21.25 between 10 and 35? Yes, it is. So there is a high chance that this is correct. And in this case, yes, it is correct. What if you want to use the ratio method instead? So this is how you can do it. I'm just going to draw a line here to separate the two. So to solve this using the ratio method, assuming of course that the change in resistance is uniform, the change in temperature is an equal ratio to the change in resistance. Now remember that when it comes to ratio, it's always the change in the values, the difference in values. So if you hear me use the word change and difference, they're actually interchangeable. All right? So the difference in values. So remember, known against the unknown. So the known would be the comparison of these two first. The difference is 100 minus 0. And this will be ratioed against 35 minus 10. This ratio is equal to the unknown, which we will now compare between 45 and 0. So 45 minus 0, ratio this to R45 minus 10. So this gives us 100 to 25 equals to 45 ratio to R45 minus 10. So remember, ratios can be converted to fractions. So this gives us 100 divided by 25 equals to 45 divided by R45 minus 10. And from here you can solve this. So I'm going to simplify because this gives us 4. We're going to exchange positions this way. R45 minus 10 gives us 45 divided by 4. So 45 divided by 4 would give us 11.25. And then we bring 10 over, giving us 11.25 plus 10, giving us 21.25 ohm. And as you can see, you get the same answer. Now, let's look at another example. It is possible sometimes that they give us thermometers where the fixed points are not 0 and 100. So for example, in this question, a pressure thermometer shows a temperature of 100 degrees Celsius at 50 kilopascals and temperature of 300 degrees Celsius at 200 kilopascals. What is the temperature measured when the pressure is 300 kilopascals? So the first thing I like to do, which actually is good practice, is to write down the temperature with the matching value, in this case, the pressure. So at 100 degrees Celsius, the pressure is 50 kilopascals. And at 300 degrees Celsius, pressure is 200. The question is asking for the temperature measured, that means the unknown temperature, at 300 kilopascals. So for the unknown temperature, I'm going to represent it with theta. And the equivalent pressure is 300 kilopascals. Now all this while, I've been showing you how to solve the questions using the formula method and the ratio method. In this case, can we use the formula method? It's a little bit trickier in this case because the two fixed points on this pressure thermometer are not the same as with the mercury thermometer. The mercury thermometer has fixed points of 0 and 100 degrees Celsius. But for this thermometer, it's 100 and 300 degrees Celsius for the known values. So we can't use the formula as is. It is still possible, but we need a lot of modification. So in order to show you the modification, I'm going to start off first by writing the original formula. So the original formula for the mercury thermometer is theta equals to L theta minus L0 over L100 minus L0 times 100 degrees Celsius. So first thing we need to change obviously is L, because the pressure thermometer doesn't measure length, it measures pressure. So we're going to change all the L's to P. Where in this case, P is the pressure. Next, the fixed points are not 0 and 100. So the lower temperature that is known for this thermometer is 100, not 0. So we're going to change the 0 to 100. And for the upper fixed point of 100, for this thermometer, the higher known value is 300. So we're going to change this to 300. Now, the tricky part is this temperature. It is not a straightforward conversion of, 100 change to 300. No, the 100 degrees Celsius here is not the absolute value of the upper fixed point. That means we don't take 100 because it's the upper fixed point. The value of 100 here is actually the difference between the upper and lower fixed point. So the difference between 100 and 0 degrees Celsius is 100. That's why it's 100 in this case. So what goes here should be the difference between the upper and fixed point. That means in this case, it's a difference between 100 and 300. So that's why we don't write 100 and we don't write 300. The difference here is 200. So we're going to write this value here as 200. But that's not the end of it, because this is showing us the difference between 300 and 100. Because this 200 starts from 100, add on 200 to get 300, this value has to be added with 100 degrees Celsius, which is the lower fixed point. So the reason why we don't see this kind of complicated formula with a mercury thermometer is because our lower fixed point is 0. So it makes things so much easier. You minus 0, you plus 0, you're going to get the same number anyway. But if you don't start from 0 and you start with another number, this is a modification that needs to be made. So again, why we plus 100? It's because this number is the difference between the upper and lower fixed points, and because the lower fixed point has a number, you need to add that lower fixed point to the overall value. Come, let me show you how this works. So now that we have this formula, let's substitute the values in. So P theta is the pressure at theta, so that's 300 kilopascals. P100 is 50. P300 is 200. And again, we're going to minus this with 50. We're going to multiply this with 200 degrees Celsius, and the overall must be added with 100. So solving this, we will get 250 divided by 150 times 200 degrees Celsius. We'll add this with 100. What we will get is 333.33 degrees Celsius. This needs to be added with 100 degrees Celsius, giving us 433.33 degrees Celsius. So if you'd like to check, is this value correct? Compare this against the original known values. So as you can see, the pressure for theta is 300. This is higher than the pressure at 300 degrees Celsius. You can see that this is 200, this is 300. This means that theta should be greater than 300. So looking at this, at 433.33 degrees Celsius, it is higher than 300. So most likely this is correct. What if we want to solve this using the ratio method instead? So I'm going to draw a line here to show clearly the demarcation between the two methods. So we want to solve this using ratio method. Remember that the ratio method is based on the difference in values. So for the difference in values, we're going to compare the difference of temperature against the difference of pressure. We need to compare the known against the unknown. So the known would be the first two lines. So the difference between the first two temperature values is 300 minus 100. Now, if you want to write the value of 200 straight away, actually you can. The reason I'm writing this out in full is for the benefit of those who need to see how we got the values. If I wrote 200, you'd be like, where did they get the 200 from? So that's why I'm writing it out step by step, 300 minus 100. But if you know the value straight away, you can just write the value straight away in your working. So the same thing also for the difference in pressure. It's 200 kilopascal minus 50 kilopascal. I'm just going to write 200 minus 50 here. Again, you can just write 150 straight away if you are able to get the value. So this is the known value. To compare the unknown value, we would take the difference between theta and another line. Now, you can actually take the difference between the second and third line, or even the first and third line. Whether you use the difference between theta and 300 or theta and 100, you would get the same value. You don't always have to compare it against the first line. So for this calculation, just to prove this to you, I'm going to take the difference between 300 degrees Celsius and theta degrees Celsius. So to take the difference, we need to minus the values. The question now is, do we take 300 minus theta or theta minus 300? Do we take the second line minus the third line, or the third line minus the second line? Now let's say we don't know whether theta is greater or less than 300. We would of course prefer to take the greater number minus the lesser number. So because we don't know whether theta is more than or less than 300, let's look at the values that we do know. We know the pressure, 200 and 300. And as you can see, 300 is greater than 200. The third line is greater than second line. So this tells us that theta would be greater than 300. So let's take the third line minus the second line to make it easier for our calculations. Okay, whoops, there's not enough space. I'm just going to put it on the next line. Alright, and now let's solve this. So we'll have 200 ratio to 150 equals to theta minus 300 ratio to 100. We're going to change the ratio to fractions. So this gives us 200 divided by 150 equals to theta minus 300 divided by 100. So theta minus 300 equals to 200 divided by 150 times 100. This would give us 133.33, and then bringing 300 over to the other side. So this is 300 plus 133.33, giving us 433.33 degrees Celsius. So this is how we can use the ratio method to solve this kind of question. So whether you want to use the formula method or ratio method is really your choice. As you can see, my preference is actually the ratio method because you can use this to solve any kind of thermometer question regardless of whatever upper or lower fixed points values are given. So just to finish off, let's go into thermocouples. Don't worry, for this thermocouple question, it's quite straightforward because we have the cold junction placed in melting ice and a hot junction placed in boiling water. If you don't know what a thermocouple is, I will explain more details about thermocouple thermometers in a separate video because that could take quite long. So for now, I'm just going to go through how to solve this question. So thermocouples work based on the difference in temperature causing current to flow, and this is shown in terms of the voltage. So in this case, the voltage is 1.5 millivolts when the two junctions are placed in melting ice and boiling water respectively. So for thermocouples, it's much more straightforward because there's only one voltage value. We know that melting ice is 0 degrees Celsius and boiling water is 100 degrees Celsius. I'm just writing this as a reminder. So the difference between these two is 100 degrees Celsius and the voltage is 1.5 millivolts. They want us to find out the voltage of the thermocouple at room temperature, which is 25 degrees Celsius. So we have an unknown voltage here. I'm just going to write this unknown voltage as V25. So in this case, if you're looking, can we use a formula? You can, but there's nothing to minus. Because we have the values like this, and I've written this in ratio method, let's just use the ratio method straight away. So we're going to write this side by side. 100 ratio to 1.5 is equal to 25 ratio to V25. Because if the change in voltage is a uniform value, the ratios of the known to unknown will also be equal. That's why we can just use the ratio method straight away. So writing the ratio in fraction form, 100 divided by 1.5 is equal to 25 divided by the unknown voltage, V25. So making V25 the subject, we would get 25 times 1.5 divided by 100, and this would give us 0.375 millivolts. And again, if you ever just want to verify, could this number be correct? Let's look at the known values. So V25 is the voltage at 25, and 25 is less than 100 degrees Celsius. In fact, it's a quarter of 100 degrees Celsius. So that means V25 should be less than 1.5 millivolt, or in other words, a quarter of 1.5. So if we were to look at this number, yes, this number is less than 1.5. In fact, it is exactly equal to a quarter 1.5 millivolt. So most likely this value is correct. And that's how we solve questions for uncalibrated thermometers. So if you found this video to be educational and helpful, please click like and subscribe for more free physics lessons from your physics teacher, Miss Hu. If you'd like access to notes, quizzes, and syllabus updates, please visit my website at physicsrocks.com. And if you'd like to help me keep making free educational video lessons and lab practicals, donations are welcomed at my Ko-fi page. That's ko-fi.com/physicsrocks. Happy studying!